You're listening to EE Times On Air, and this is EE Times Current. I'm Taylor Marvin. Welcome to Brains and Machines, a deep dive into neuromorphic engineering and biologically inspired technology. In this episode, Professor Chris Eliasmith talks about how his work has taken him from basic research and cognitive modeling to helping spin out a low-power AI chip. Your hosts are Dr. Sunny Bains of University College London and Dr. Giulia D'Angelo of the Czech Technical University in Prague.
Welcome to Brains and Machines. I am Giulia D'Angelo.
And I'm Sunny Bains.
In today's episode, Sunny will be talking about technology up and down the hardware-software stack with Professor Chris Eliasmith of the University of Waterloo and Applied Brain Research. After the interview, we will be talking to Ralph Etienne-Cummings from Johns Hopkins University about the issues raised.
Thanks, Giulia. As you'll hear, Chris has been trying to build a brain one way or another from the 1990s. Since then, he and his team have built up a suite of tools to help them and the wider community do just that. These include NEF, the Neural Engineering Framework, SPAWN, the Semantic Pointer Architecture Unified Network, and Nengo, the software that allows you to build NEF networks in Python, and more. In this episode, we'll find out what these are and how they allow neuromorphic engineers to perform cognitive modeling. There are links to his work and some of the specific papers we'll be discussing on our website. You can check them out at brainsandmachines.net. Chris Eliasmith, welcome to Brains and Machines.
Thanks. It's fantastic to be here.
Can you start off by telling us about your technical background and how you got involved with cognitive modeling?
Absolutely. So my technical background, I guess, goes back to my undergraduate degree, which I did in systems design engineering at the University of Waterloo. After that, I then moved into less technical areas. So I did a master's degree in philosophy and a PhD in a philosophy program that focused on philosophy, neuroscience, and psychology at Washington University in St. Louis. And what brought me to cognitive modeling in particular was actually a lifelong interest in understanding how people work. I remember very clearly sitting with my grandfather in a mall, and we were watching people go by, and he would comment just on like, what is that person thinking? Or how is that person making the decisions they're making? Or I don't know, it was something that just caught my fascination. And all through my undergraduate degree, I took a lot of extra courses in philosophy and psychology, and they really became what I was fundamentally most interested in, which is why I pursued those subsequent higher degrees in essentially cognitive science from the philosophical perspective.
Very interesting. So, of course, you have built your own cognitive model. You're best known for SPAWN, which is the Semantic Pointer Architecture Unified Network. So that's a lot to take in just in one name. Can you start by talking us through what you wanted to achieve with SPAWN and then go on to explain to us what a semantic pointer architecture is and how it's used in this case?
So it's a fairly long story, but I'll try to keep it compact. The model itself comes out of trying to essentially fulfill a promise. In my career, I worked on a book called Neural Engineering, and in that book, we tried to answer the question of how do brains compute? So if I give you a function, I say, I want this function computed in a brain, what neural network do you give me back to do that? And so that book kind of answered that question. You can think of it as a kind of neural compiler. I was in the middle of writing a second book when the idea of SPAWN came to me. In that book, we were trying to answer the question of what do brains compute? So what is the specific function or set of functions that brains compute to do all of the fantastic and amazing things that they do? And in my lab at the time, we had people working on motor control, decision-making, perception, all of these different components. But cognition, of course, isn't a component. It's the integration of all of these things. And so in the book, I was explaining how you can build all these components and then you can integrate them. It will be great and you'll have this wonderful model. And then I thought, well, the most compelling way to show that is to do it. So taking all of these different components that all of my students were working on and bringing them all together in a single model, hence the name unified model at the end of that big brain model. And that was really the inspiration for building that specific model, was to demonstrate not only that these techniques could help you build neural networks that were biologically plausible that did a lot of the functions that brains did, but that we could bring them all together and essentially show that the whole is greater than the sum of the parts.
Very good. So can you talk about what some of those parts were, both from the low level and what is the semantic pointer architecture? What does that exactly mean? And also from the brain point of view. So what are the different brain elements that you were trying to join together, and how did that work?
So the semantic pointer architecture is an architecture, and that means that it proposes a bunch of different components and a way for those components to communicate with one another. It doesn't propose all of the components, right? It's incomplete architecture, I think it's fair to say. But it does propose things like a working memory system. It proposes a decision-making control system, which is often associated with the basal ganglia. Working memory shows up actually in many different parts of the brain. It proposes a particular way of structuring the perceptual hierarchy, the visual hierarchy. It proposes a particular way of executing motor commands, going from sort of very high-level, more abstract descriptions right down to driving the muscles. So these are a bunch of example components in the architecture. We describe how they go together. So the basal ganglia sits there and monitors many of these cortical functions. There are parts which are mapped onto the cerebellum from the motor system. And the architecture proposes how all of them are coordinated together in order to execute an overall behavior of some kind. When it comes to mapping that onto the brain, as I said, things like working memory, you actually find them in many different parts of the brain, right? So you have working memories that are vision specific, that are auditory specific, that are more motor related, that are more about tracking a task in the environment, so more executive types of working memory. And every part in the model that we construct based on that architecture, we map to a particular part of the brain. We point to data that shows that this kind of function is found in that part of the brain. And so we go from the kind of abstract description of an architecture right down to how each of these components map onto particular brain areas. The other key part, and where the name comes from, is talking about how these components communicate. And this is where the notion of a semantic pointer comes in. So this is an abstracted characterization of neural activity. The idea being that we can talk about abstract vectors. So these are not vectors of neural activity, but they're vectors that are mappable onto neural activity. And those vectors carry information around in the brain in a particular way. And so that's where the notion of a semantic pointer comes from. I think that the easiest way to think about them is they're just compressed representations of information that are before them. So the semantic pointer at the end of the visual hierarchy is a lossy compression of the visual information that's earlier in the visual hierarchy. And the reason you want to do that is because then you can move that vector around. You don't have to move an entire image representation around. You can move a compressed representation around more efficiently. You can send it to working memory. You can do many other things with it much more compactly than you would if you tried to re-represent all of the information that is flooding the brain. So those are the components. There's that architecture with a bunch of different example modules. There's a particular way that they all communicate, and all of that is mappable onto neuroanatomy and neurofunction. So those vectors are passed around through spiking activity in each of those components.
So talk about the specific experiments that you did, the specific tasks you got it to perform and how it behaved.
Certainly. I'll have to pick tasks. So the original SPAWN model did 8 different tasks. SPAWN 2 did 12 different tasks, and one of those tasks was instruction following. So it could follow instructions to do many different tasks that you basically told it to do. And we're working on SPAWN 3 right now, and it is going to do all of those tasks plus many more, actually much more difficult tasks. So I'll start with SPAWN 1 just to give a sort of sampling of the kinds of things that it could do. So it could do very simple things like classify inputs, right? So you give it a bunch of different numbers, and it could draw out with its arm which numbers you had shown to it. It could count. So you could show it a 2 and say, what number is 5 after 2? And it would write 7. It could perform adaptive motor control tasks. So you have it writing those numbers out, but then you put it in a force field, and that force field is basically making it strange to move the arm. And so the writing looks bad, but over time it can adapt to that force field just like people can, and it can start writing out numbers correctly again. It can do intelligence tests. So you can show it many different sets of inputs with different patterns in it, and then basically say, what pattern did you see, and can you complete this task to finalize a pattern? So this is called Raven's progressive matrices. It's a well-known fluid intelligence test, and we made a version of that. It's not the full test that we could show to the model, and it could answer all those questions, and it could get a score similar to your average undergraduate student. So ranging from motor control, perception, decision-making, and things that I think are undeniably cognitive, right? So I've listed, I think, 3 tasks and there, many, many more.
That's really interesting. It must have been quite exciting when you saw this working.
Yeah, absolutely. Yeah. In some ways, it wasn't surprising to us that it worked because we were very confident that each of the components worked. But I think actually what was most impressive to me was to show that model running to other people, to neuroscientists, for instance, and having their eyes widen and they're just like, I feel like I'm watching a brain behave. It was really a strange experience. You can watch all of the activity move across the brain. You can look at the spikes. There's no mystery about anything that's going on in there. We can record all the data you could possibly want. And a lot of it looks very biological. That was the most compelling part for me, was seeing how it affected other people when they saw this thing for the first time.
I can understand that. Okay, so let's get back to the hard stuff. So the semantic pointer architecture, as I understand it, is in the same class as vector symbolic architectures. Is that wrong?
That is wrong. It's a very common mistake and a little bit of a pet peeve of mine, but...
Oh, well, good. So correct me.
Yeah, so there are 2 issues. So issue number 1 is that vector symbolic architectures are not architectures. They're algebras, right?
Yeah.
So they're algebras. They don't have component parts. They don't have communication. So it was a very unfortunate misnaming of that set of techniques. So VSAs, we call them vector symbolic algebras in our lab because we are trying to sort of correct that issue. So they're algebras. In the semantic pointer architecture, we use that algebra for some components and some representations, but not across the board. So the notion of a semantic pointer is more general than the notion of a vector symbolic algebra vector. There's also a distinction where it's definitely a technique that we use. We use many techniques in constructing that model. It's a technique that we use a lot when we're worrying about cognitive behavior, so representing structured information and so on. It's a technique that we use even more in the most recent version of the model because we use it to explain reasoning about space, representation of space, moving around in space, and so on. But yeah, it is a sort of one tool in the toolbox, I would say, of the semantic pointer architecture for constructing brains. Yeah.
I am really grateful that you corrected me on that. So can you explain the connection between actually all of these things? So the semantic pointer architecture, the vector symbolic algebra, and neuromorphic engineering, because obviously that's always been my main interest. And it's the reason that I got to know about your work. Your group is really active at Telluride. I've spoken to your colleagues, Terry Stewart and Michael Furlong, many times. So can you talk about how you ended up being in this space with these neuromorphic engineers?
So you asked a 3-part question, or actually 4 parts. So relate the vector symbolic algebra, semantic pointer architecture, and neuromorphics, and then how did we come to get involved in the neuromorphic side? Let me jump on the first part, the relation between those 3. So to keep it succinct, neuromorphic engineering, building hardware that's power efficient and reflects some of the computational principles in the brain, that depends on having good algorithms to run on that hardware. So how do you organize that hardware so it executes a function or behavior that you're interested in? My work has been really focused on the algorithmic side, building algorithms that will run on neuromorphic hardware, because typically neuromorphic hardware uses event-based processing, and all of the models that we build are spiking. So they're event-based as well. So that's that relation. We use the semantic pointer architecture and the neural engineering framework and the vector symbolic algebra. Those are all ways of generating algorithms that can run on that hardware and realize the potential of the hardware. The relation between the semantic pointer architecture and vector symbolic algebras is that in the semantic pointer architecture, we have, for instance, a working memory module. As I mentioned, semantic pointers are essentially compressed representations in a vector space. Vector symbolic algebras define one type of compression. So there are many different types of compression. Vector symbolic algebras specify one type. They specify it by picking some operators that are used to combine vectors in the vector space to give you new vectors. So we exploit that in things like the working memory module and in many other places in order to specify which vectors are represented in that part of the brain and potentially how they're constructed, how they relate to each other, kind of at an abstract level. So I mentioned before that we think about vectors as being mappable onto the neural activity. So you can do a lot of things in that vector space before you map them onto the neural activity. Vector symbolic algebras are great for that. because they're algebras, we know how to map them onto spiking neural activity. So you can imagine if I specify an algorithm using a vector symbolic algebra, I can import that into the semantic pointer architecture to make it part of a larger brain model, and I can take that entire thing and run it on neuromorphic hardware. Hopefully that answers the first part of the question.
Yes, it does. So on to the second. So how did you start getting involved with the neuromorphic community?
Actually, before the semantic pointer architecture was around, we had this thing called the neural engineering framework. And this was, as I mentioned, answering the how question. How does the brain compute a function? So we were using this to compute all kinds of different functions, building all these spiky networks. And the thing you run into very quickly is that your computer sitting on your desktop is slow when it tries to run those algorithms because it's not built like a brain. In early days, I was looking around for ways to run our algorithms faster. Coming across neuromorphic hardware, it's kind of not a surprise when that's what you're looking for. So we started to talk to people in the neuromorphic community, and they ran across our method for generating algorithms. So how can I take this high-level algorithm and embed it onto my neuromorphic hardware? That's exciting to them. And so they invited us to Telluride. So I want to say like 2010, the first one that we went to. And we had been to other things like NeurIPS and places like that. But Telluride, that was where neuromorphics is the focus. We got to talking to many different people building many different neuromorphic platforms. I think in the end, pretty much every neuromorphic platform has had our neural engineering framework used as a way of programming it. I'm sure that's not everyone, but the majority for sure. And so we've really become embedded there in some ways, right? So this is very exciting to us because we can build these algorithms and then run them efficiently on this hardware, which is fantastic. And it's been, I believe, also helpful to the community because they have ideas about the kinds of functions they'd like compute, and the NEF provides a method for mapping those functions into spiking neurons and hence onto event-based hardware.
Right. Now, I've heard some nice things about Nengo, and I've seen some of Terry's nice tutorials on them. It looks like it's a really sophisticated interface for neuromorphic hardware to be able to do some nice stuff. My question is that just because it's a nice interface doesn't necessarily mean that what's going on under the hood is going to be efficient. So I guess what I'm getting at is even if you can tell it what to do efficiently, is the underlying process the best way of getting that function to run on that machine?
Right. There are a couple of points there. So first, thank you for complimenting Nengo. We do think it's a great tool. Lots of people use it. It's something that we have put a lot of time and effort into. I do agree with you that I think it has a very nice interface, so it makes it fairly simple to specify these problems. The question of efficiency is actually an interesting one. So one thing that it does is it kind of natively implements this neural engineering framework. And one thing about the neural engineering framework is it actually is more efficient than most neural simulators because of how it decomposes weight matrices. So not to get into too many details, I guess, but if you usually specify your neural network as a connection between, let's say, two populations, and you've got a big weight matrix in the middle, then the number of operations you have to do is the size of this square matrix. So it's square in the size of the vectors that you're passing through this matrix, essentially. What we do in the neural engineering framework is we decompose that into two vectors that you can basically do an outer product of to reconstruct the matrix. So when you do that, now you have way fewer operators to perform. You have just n as opposed to n squared. What that means is when we're running on normal hardware, it's a very efficient way to actually simulate these spiking neural networks. It doesn't necessarily mean that for neuromorphic hardware. In neuromorphic hardware, it depends on how it's been built. So we've worked with people to build chips. So Kwabena Bowen, who you probably know, we worked with his team to build a chip which essentially implements that kind of decomposition right in the hardware. And so there's a very easy mapping from the simulator onto that hardware. Other chips assume that you do have a full weight matrix, right? And so we can always construct the full weight matrix and run the model that way. And if it's efficient to do that, then that hardware will be efficient. Or sometimes you can coerce things that are written to expect a full weight matrix to work with these decomposed weight matrices, and you can improve the efficiency of the hardware sometimes. So yeah, these are all ways that you can take advantage of some of the efficiencies kind of built into the neural engineering framework. Does it mean it's the most efficient? Not necessarily. One thing you can do is you can take a neural engineering framework network and then further optimize it, right? So you can run backprop on it, or you can do other kinds of optimization if you think that's going to improve the overall efficiency of the network. I will say for the most part, we haven't found that it's something that's particularly important to improve the sort of efficiency of networks and so on. But regardless, it definitely is something which you could do if you were really trying to push the efficiency of the network. Overall, the thing that typically seems to be most important is to turn the algorithm into a format that can run on the hardware. So if it runs on the hardware, it's parallel, then you're taking advantage of the way the hardware was intended to be run. That's where your biggest efficiency improvements are coming from.
Good. Now, one of the things about the way NEF works, as I understand it, is that it is a rate-based population code. And so the idea is that instead of storing a value as an analog number or as a spike time or something, it's stored over a set of neurons. And some people have said that that can be inefficient. Can you talk through the way that works?
It is not a rate-based population code. Yeah, the rate-based thing is a really strange claim. People have definitely said that. It's not true. Often when we're trying to explain it to people who don't care about the rate versus timing debate, we'll do that as a shorthand, which is maybe not the best idea, but really we don't think of it that way. So we kind of describe how you can move smoothly between rate and timing codes using our methods. And so there's no preference of one over the other. If you look in the brain, the evidence seems to suggest that it depends on where you are in the brain, if it's more of a timing code or more of a rate type code. And it depends on the computational constraints. If it's extremely time sensitive and speed is the most critical, then timing codes become far more important. If it's a very noisy environment and precision in an underlying variable is more important, then things like rate codes seem to often show up. So we think that actually this is the right approach, is to have a theoretical framework that lets you move smoothly between the two. You can pick which one is more relevant, dependent on what particular functional constraints you're faced with. So that being said, calling it a population code is more reasonable, that we definitely present it that way. I will note that we talk about populations of 2 neurons a lot of the time. So these are not like massive populations that you're wasting a ton of resources on. Again, what we talk about in great detail in the book is how to set the number of neurons to be such that it captures the underlying variable with the precision required for your task, right? For the function you're trying to compute. So we always tie it back to these implementational considerations. And that's really what ultimately determines how many neurons you do or don't have, whether you're using short or long time constants for doing your filtering of your spike train and so on. And all of these map onto actual biophysical processes. So you can compare them to real biological networks and see, are the things we're building with the NEF looking like the ones that we find in the brain? And in that instance, the answer is often yes. We have not seen an instance, I think it's fair to say, where someone's proposed some network which is way, way more efficient than an NEF-built network if you build it correctly. You can build them badly and they can be inefficient. That's true for pretty much any method. But if somebody says, here's the function we want to compute, these are the good constraints, et cetera, then building an NEF network is typically as efficient as any other method, and sometimes much more.
And your point is well taken about compilers, that essentially if you end up compiling your network badly, then it doesn't matter how good your framework is, it's going to come out badly in the hardware. I'm also very interested in what you said about the moving from timing-based codes to rate-based codes with the spikes, because I have read a small number of papers on this, and that this is also what happens in the brain, that it uses rates when it needs rates, it uses timing when it needs timing. And I wondered whether you had a paper on that we could look at, that I could put in the show notes.
It's in the book in the most detail, in the Neural Engineering Framework book. The book is freely available. MIT returned the copyright to me, so people can download the book. So I can post chapter 2 or whatever chapter.
Perfect. And we will put that online. Excellent. So that's really interesting. So you feel that the networks that you come up with, although it's possible that they could be pruned further, essentially, once you've created your base network using the Nenko framework and NEF and whatever compiler you happen to be using, and then whatever hardware, that nevertheless, that's going to be a good first approximation of what the best network is for the job.
Exactly, yeah. And we've done explicit experiments where we've built a starting network, seen how accurate it is and how many resources it's using, and run optimization, like run things like backpropagation or pruning or what have you. And yeah, it works well. So you can get improvements, but typically the improvements aren't massive. I will say that the NEF networks are sparsifiable in the same kind of way that typical deep learning networks are. So if you take a deep network, it's often not very efficient from the perspective that you can do massive sparsification and it still works as well. And that's kind of similarly true.
So what you're saying is that the NEF networks are not sparse in the way we would like them to be in order, for instance, to do 3D networks and have activation sparsity and all of that kind of thing.
They can be, for sure, right? Again, this comes down to all kinds of choices while you're doing the compilation. So the default NEF network method for doing weight optimization was using least squares. So that's basically doing an L2 norm, but you could do L1 norm or L0 norm, and you get much more sparse weights. Again, these are just kind of like parameters in the compiler. And you can also generate a non-sparse network and sparsify it afterwards. All I was trying to point out is like all the standard techniques for tweaking your compiler apply in this instance. And there's definitely no evidence that the starting network is any less efficient than the starting network you get out of any other default method, like doing deep learning or whatever.
Your group has also come up with Legendre memory units to represent time. Listeners may remember that BrainChip have been using this approach as well. Can you talk about what they are and why they're useful?
Sure, yeah. So this, just to be clear, this is jumping ahead about 16 years. Right? So 16 years later, after the neural engineering framework, we were working on this problem of how does the brain represent information over time? Really interesting problem. And with my student, Aaron Volker, we were trying to start at first principles. Can we formulate a problem which is simple enough that we can actually make some theoretical progress on, and that ultimately leads into some insight into what the brain does? And it turned out, yes. So if you formulate the problem that the brain is trying to solve as one of remembering all information over a delay, so just have a signal that's coming along and you're just trying to delay that signal by some length of time, that turns out to be a problem that you can write down the differential equation that is like, here's the optimal solution to that problem. We call this the Legendre delay network because it's specifically focused on a delay, and it turns out to be a linear network. And so you can prove that it's efficient. You can use it to predict time cells. So these are cells that people have found in the brain, in the hippocampus, and actually now all over the brain, which are related to representing time and exactly when events happen during tasks and all these kinds of things. So we define a dynamical system, use the neural engineering framework to build a spiking neural network of the dynamical system, and then look at the temporal responses when we run it through experiments that are like the ones they run the rodents through, and you find cellular responses that look like the ones that the rodents also exhibit. So we were really working on like, how does the brain represent time? But we also came to realize that, well, this is a problem in machine learning. Time series is like a massive area of research, and it's, really hard, and people have all kinds of different recurrent networks. So there's LSTMs and GRUs and a million variants on each of these. Transformers are now what people are using, where it's not a recurrent network, but it kind of spreads time out in space, so you can just process stuff in a feed-forward way. So all of these different approaches. And so we started applying this core dynamical system to these problems. And so the obvious thing to do, I think, was basically you take that linear system, so this is the thing representing the temporal information, and then you put a nonlinear layer afterwards, so you can then manipulate that temporal representation however you want. And you'll learn that using normal backprop. And that's what we call the Legendre memory unit. More recently, people have taken that exact same structure and called it a state space model for obvious reasons, because basically having a linear dynamical system and then a nonlinear layer, that's a state space model. And that's what BrainChip is using, for instance. And so when you add that nonlinear layer, we did that, and then we started comparing it to all these other methods that people have proposed for dealing with time series, and we found that it outperforms them all, often by huge margins. So we found tasks where the LMU would use 650 times fewer parameters to get the same performance as an LSTM. So just massive difference. Even for large language applications, we wrote the first paper that applied state space models to language modeling. And we showed that with basically half the parameters of a transformer, you could get the same performance. So again, really nice improvements in efficiency using this Legendre memory unit or state space model.
So that's great, but now I feel bad that I made you skip 16 years. So was there some important project that I haven't talked to you about?
The stuff in the middle was basically the spawn work. So there was that neural engineering framework book. The book came out in 2003. We started developing the framework in the late 90s. Then we applied it to many, many different brain areas. And then in about 2010, I thought it would be great to bring all this together and integrate it. And that's what resulted in the semantic pointer architecture and the How to Build a Brain book. And so that came out in 2013. 2012 is when we published the spawn model in Science. And that's also chapter 7 of that book. So we have covered all of that stuff.
All right. I feel better now. I thought I'd missed something important.
No.
Okay, so can you say something about what you're working on now and new projects or extensions of old projects that are on the horizon that you're excited about?
So I think there's like two things I would love to talk about. One is the evolution of Spawn, right? That's really what we're focusing on now and forward looking. So it captures a lot of what I think we're going to be doing in the lab. The other thing I'd like to talk about is applied brain research and exactly what they're doing. So let me start with the first one. When you look at Spawn, as I mentioned, a lot of people were very impressed by it, and that was definitely a source of pride for us. But of course, it's very limited. So it's an eye that's staring at a screen. The eye can't move. It has an arm. The arm can move, but that's its entire world is moving an arm and staring at this blank screen. So what we wanted to do with Spawn 3 is something much more challenging. And that is basically take that brain and put it in a body in the world, make it embodied. And when you do that, things get much, much more complicated. Now, of course, the reason we wanted to do that is because we feel like we have some really interesting techniques for dealing with things like spatial reasoning, being able to understand where you are, remember where things have happened, navigate around, and so on and so forth. And a lot of that work comes out of some extensions to the semantic pointer architecture, extensions as in we did them after the book. And actually, this is something that we did at about the same time that we were doing the LMU. And that's look into what's called fractional binding. So basically, instead of just binding these vectors together using our preferred vector symbolic algebra, we can partially bind them. So you can like half bind them or quarter bind them. So anyways, the math makes sense. And what it lets you do now is represent basically continuous slots, or you can put information in a continuous space, i.e. a map. So first obvious place is look at hippocampus. We showed that we can replicate all the standard cell types you see there. So grid cells, place cells, border cells, boundary vector cells, object vector cells, all these kinds of things that you find in the hippocampus fall out of these models. We can use them in systems that let you basically explore an environment, do self-localization and mapping. And that made us really excited about taking that entire way of representing the world and continuity in the world and embedding it into the Spawn model. So now Spawn has a body, can walk around. It's performing tasks that people perform in spatial reasoning, moving through environments, and so on and so forth, while also being able to do all the previous stuff that it could do. So I think that's really exciting. And we've been working at that project, but it's definitely a work in progress still. Hopefully we'll have something that we can publish in 6 months or so.
You've already done the SSP SLAM paper, though,
correct,
right?
Yeah.
So it sounds like that was one of your first steps into this area, yes?
Yeah, so that is forming the sort of foundation of what the Spawn model is going to do with respect to moving around in an environment and all that kind of thing. It's all simulated, right? We're using Isaacson, which is kind of a standard physics robotics type simulator to do this, but it definitely cranks up the complexity and so on. And that paper that you mentioned is forming the core of the navigation and hippocampal model systems. And so that's really exciting. I mean, the other thing that I think is very exciting there is that those same representations are representing continuous space. So you can think of them as a map. You can also think of continuous functions as probability density functions. And so we have a whole slew of work, again, some of which we hope will be included into the Spawn 3 model, which lets you reason about uncertainty in very natural ways, implement sophisticated Bayesian optimization algorithms, again, in a very biologically plausible way, and much more efficiently than you typically do. And so that's another whole line of work, is taking these same representations and exploiting them along this kind of uncertainty probabilistic direction. So that's, I think, really got our future research pointed in an exciting and interesting direction. So the other part, Applied Brain Research is a company that was spun out of my lab. And really the key idea there was initially to take the Nengo software and all this neuromorphic hardware, which was going to be commercialized. So you had large companies like IBM and Intel and so on building neuromorphic hardware, basically provide the software stack for that. That's something that never really materialized, I think it's fair to say. But the company, very successful doing a lot of advanced AI work for big customers. And ultimately, when we invented the LMU and state-space models, we realized that, okay, this is something which can have a really significant commercial impact. It will let us solve all of these problems like language modeling, speech recognition, anything that's a time series much more efficiently, especially given our neuromorphic background, if we have hardware that natively runs that algorithm. And so for the last couple of years, that's what we've really been focused on, is building a chip that can natively run state-space models, run it extremely efficiently because it's specifically designed to do that, and fabricate that chip and go to customers and start getting into all the many different products that you might be interested in having that in. So that's something that we're really excited because we just got the chip back for it at the end of August. We got the chip back. We tested it, and we had it up and running and setting world records in sort of low power running state-based models within a week and a half.
Talk more about this chip. I'm very interested.
Yeah, so it's not a neuromorphic chip in the sense that it's not event-based. It is a neural accelerator, so it has compute right near the memory. The memory is actually a little bit exotic. It's called MRAM, so magnetoresistive RAM, which means that it's non-volatile. So you can load your network on there. You can basically leave it shut off and it draws almost no power until you need it. And then it can run the model, which is really cool. So yeah, we're able to do full speech recognition. So I could be sitting here basically typing out everything that I'm saying in about 100 times less power than other edge hardware that's available on the market. Under 30 milliwatts, we can have a thing there that's typing out whatever language you're speaking in. We can do other things with it too. We can use it to control a device, right? So you can basically tell the device what you want to do using natural language. You don't have to memorize keywords or key phrases. You just say what you want. We're also working with customers who want to use it to do things like monitor your bio signals, your heartbeat, your O2, your sweating, anything. You can monitor all that and do on-device inference about the state of the person, warn them that they're going to have a seizure if it's EEG, or that they're having some kind of heart palpitation or what have you. And we just started our early access program. So we're working with customers, getting the hardware in their hands, helping them integrate that into their applications. We're super excited about what this chip can do. It's just kind of blowing the competition out of the water from a power and efficiency and performance perspective.
Very nice. I look forward to hearing more about that in the future. But for now, Chris Eliasmith, thank you so much for coming on to Brains and Machines.
My absolute pleasure. Thank you very much, Sunny.
Thank you, Sunny. So this interview is difficult. There's lots of things, and I'm very biased in this episode because I collaborate a lot with Michael Furlong, Nicole Dumont, Terry Stewart. I want to mention them, and they're amazing. And I think the leaders set the basis for the lab. So this speaks a lot about Chris. And for more about Chris Eliasmith's work, please go to brainsandmachines.net. And now we welcome back our regular commentator, Professor Ralph Etienne-Cummings from Johns Hopkins University.
Hi, Sunny. Hi, Giulia. Happy to be back again.
So despite lots of difficulties, right, throughout the years, I love when I see that the research of someone so experienced like him, it's so coherent. I was thinking, listening to him, maybe we need a set of brain functions which we can standardize on. Do you think that we need to try to get to the point that we have some sort of set of representations, a set of functions somehow to do complex things as he's doing?
So I think that's a fair idea or request or thought as far as how do you standardize the different methodologies in order to understand which one works and which one doesn't work, and how do you compare them. I mean, if you look at SPAWN, the system that he talked about, there's so many pieces there, right? And each one of them is being published maybe a little bit differently by themselves, but the whole entire system is so complex, right? So how does one come up with a way to basically say, hey, Ralph's version of SPAWN does this well, and Chris's version of SPAWN does that well, and Giulia's version does that well, and so on, right? But unless we have a common set of problems that we're attacking, that is very difficult. And I think that's where you're going with your question, right? Is this notion that how do we make sure that we can truly compare apples to apples and oranges to oranges? And that's always difficult in these big systems, in my view.
Yes, for me, I've seen SPAWN for the first time, unfortunately, this year in Telluride when I met Chris, and I was scared because I was like, oh, what do I do? What do I do in my research? He has done lots of things, right? So that is actually scary, but I'd love for me to install everything and try to work on it with my students. But this may be linked with another question that I have, which is SPAWN 3. And at some point, we need to link the brain to the body, which I think that is the only thing that is really missing to it. And this will open, a new set of things to do, right? Because then there is interaction, there is sensory motor contingencies and links and so on and so forth.
So it would be useful for SPAWN to be some kind of a brain in the cloud, so to speak. Then you can apply your problem to it and see how well your problem gets solved by it and whether it matches the neurobiology and the physiology that you're seeing. And I can do my problem on it. So it becomes essentially a common tool for the community, right? We've talked about that a number of times as being kind of a valuable thing. You think about, what Andre Van Schaik was trying to do with Deep South is this common tool that's supposed to be in the web that you can send problems to and check it out and see how well it works. And I think that Spinnaker also has that same intent. It seems like the chips that Chris is implementing is not that. Those chips are intended for local, embedded, fast computation, high efficiency computation on the edge. But somebody should take the entire Spiron architecture and implement it entirely in hardware somewhere that folks can get access to. Maybe that's already existent. But Sunny, did you get a sense that that's there already? Or is that something that's still to be done?
No, I'm ashamed to say I had not thought of that. That actually is an interesting idea. It might be a good use of the kind of technology that he's building. I guess what I wanted to say about it, just sort of thinking back about the confusions that I had or the uncertainty I had when I was reading through his material and listening to him talk, it has to do with the stack, really, and where we are on the stack when we're talking about the population codes and what Spawn does, what Nengo does, and how many layers it is up from the hardware. And I worry that I'm not clear enough on how close it is to the bottom layer. And when you heard me talking in the interview about my fear about it not being very efficient, it's because I fear that it's so much of a mathematical abstraction that it needs neuromorphic, but neuromorphic doesn't necessarily need it. That essentially the way the maths works, as far as I understand it, which is not hugely well, but I tried to look into this before the interview. The way the maths works, Nengo really needs good parallel architectures like the ones that neuromorphic can offer in its hardware. But there are lots of ways that we can do things that don't use the same variety of maths. And so that's why I'm still not happy that I understand that. But what he's done at a higher level, at the bringing different cognitive systems together level, I think that's kind of amazing and impressive. It's just how far it is in that stack.
Yeah, so I think here we need to say one important thing, in my opinion, is that he's giving us an entire ecosystem. Whether you like it or not, so whether you like to have that specific approach of vector symbolic algebra or whatever you want to use that they provide to you, it's an entire ecosystem. And that's the important of it, in my opinion, right? Because you can go there and play with it. Then another thing that I want to tell you is that I talked with Michael Furlong and Nicole Dumont, and I think I can assure you that yes, it does run on Spinnaker. There's lots of backends to run Nengo on Spinnaker, and I'm using it too. I have a bachelor student that made Nengo running on Spinnaker easily in 2 weeks. So I can tell you that what they're doing together is giving the neuromorphic community or whatever neuroinspired community an entire ecosystem of tools that you can use. Then, whether you want to use vector symbolic algebra or Legendre unit, whatever, it depends on you if you like the idea to use it. But I think it's really important, and we need to stress out that they are giving an entire ecosystem to everyone.
My problem is not with that, right? I think that's a great thing. The question is whether it's the right ecosystem for neuromorphic. And I'm not saying one way or the other. I don't feel confident enough to know. What I would say is that I still have concerns about the efficiency. One of the things we're trying to do is funnel from a higher level of neurons to a lower level of hardware efficiency so that we can get things done. And if we're using the wrong models higher up, it will cause more bottlenecks further down. So I don't have a problem. I know that it works. I also very much admire all of the Nengo, Spawn, Waterloo people. I think they've done great work. So don't get me wrong about that. It's just, I'm not sure whether it's necessarily the right model. And I haven't also seen so many people rushing to say, this is what we needed to do the most efficient stuff.
So maybe the emphasis on efficiency is not necessarily the right emphasis at this time. We are still at the stage where folks are inventing n different numbers of neuromorphic hardware flavors, right? I mean, I have my own, he has his own, they have their own, and so on. Then the question is there a unified interface that allows us, firstly, to compare different technologies, right? Different implementations. And I think Nengo has been that. Because, like Chris said, Nengo has been implemented on everything from brain drop to Spinnaker and so on and so forth, right? So that's a really good thing. Number two, I think, is that the reason like Loihi took off is because Loihi had a nice interface that people could tap into, right? And now that Loihi has seemed to have gone quiet for a bit, having the Nengo infrastructure available for any platform, I think is super valuable. And whether or not Nengo is the Microsoft operating system, DOS, of the neuromorphic space or not, that's the part that is still an open question.
I think there are two things I'd like to add to that. One of the things that would really help us here is Brad Imony, who we talked to a couple of months ago, or somebody else having some kind of theory that could let us tease out whether things are efficient or not, whether this is the best way to do it. One of the things that you always hear me complain about, and I know I get very repetitive, is the idea of simulators. So just because you can simulate something doesn't mean that you would necessarily want to build it that way. And that's one of my concerns. The other thing is I once had a long conversation with Terry Stewart about compilers and the problem of having some low-level hardware and trying to take Nengo and put it on top of that hardware in the most efficient way. And how efficiently that computation can be done is entirely dependent on how efficient the compiler is. So I think these things are going to evolve over time, but I think theory is going to help us to do that. And I don't think we have that theory yet. So it's hard to tell.
I imagine that Chris would push back on that statement. His theory is the one, and at the end of the day, I think we just need multiple higher level folks thinking about it from a general perspective, right? The Brads of the world. And the Gendre unit seems to be really, really, really useful. It seems to have, some of the properties that are ideal for some of these time series. The interesting thing is, I kind of did a quick little survey because that paper came out in 2019. And I was wondering whether others have been using it, and I don't see it as often. So why? Now, he's making the argument that this can completely revolutionize LLMs and how that's done in terms of an efficiency perspective. I would have thought that that community would have jumped on it and say, why spend the amount of power that we're using, the number of variables that we have? This approach gives us the same performance for much fewer variables and power. So why hasn't happened? So I don't know the answer, right? I'm just trying to understand where we stand from that perspective.
Yeah, if you can map these efficiently onto the hardware, then it's going to work. And of course, I love the idea of the population codes. And he points out that the way that Nengo works is very elastic. You can have more neurons dedicated to a certain thing or fewer. I'm good with all of that. It's just maybe I didn't read the right papers when I was preparing for this, but I still haven't seen the numbers to prove to me that this is a better way of doing it than other ways that people have come up with. That's all I need. But I think it's great work. Don't get me wrong.
So I think that the idea of this is to go towards an abstraction, right? Where you can do many things together. Like, thanks God, I have a PhD that is a physicist and I can understand the math behind vector symbolic algebra. And I'm exploring it a lot with her, right? But maybe in one case, I saw lots of excitement for state space models and DSA lately. So I think possibly lots of things will come out, or at least possibly the work that I'm doing with my PhD and co. But on the other side, what I think, Son, is that they are not caring that much as to the lower level as you care, or in the way you care,
right,
to then do something that would work in the way you like, in quotes, right? Because what they do is to give an infinite space of possibilities to represent different problems. So I think it's impossible to match
what we like, because I like it too, right? To go very low next to the hardware.
I think it's an ethical issue, though, these days, too. I think one of the things that we don't need are more ways to burn computing power. So I think asking about efficiency when someone starts doing something, and this is not new, right? He's been working on this for, 15, 20 years now, maybe more. So you can't say this is new. But all I'm saying is these questions of efficiency have to be asked, because he might be able to come up with a fantastic programmable thing. But if you need to burn down all the rainforests in order to be able to run that full-size brain that he wants to build, then I'm kind of not interested in encouraging him to do that. That's one of the reasons why I think it matters that we talk about efficiency at the lowest level, because we've seen some great technology come, but a lot of people are really regretting it. Some of the absurdly wasteful, climate change encouraging things that we're doing. And I just think we should all have at the back of our minds, if it's not going to be efficient in the end, why are we even bothering with it? Why are we spending money on it?
Yes, but no, that's true, Sunny, right? I don't know that it's not efficient. I think it might not be the most efficient, but if it still beats the kind of stuff that folks are doing with large language models, then to me, that's a win, right?
I'm not saying that it doesn't. In fact, I would say as long as it's in the order of magnitude from the lowest power, it's still totally worth doing. Right. I just don't have those numbers. And until I have those numbers, I'm not going to be happy. Okay. So I need to understand what the implications are for power efficiency.
I would say then we have to wait for his chip that just came out, right? If he's able to do the kind of things that he's saying he's able to do on his chip, the efficiency and the accuracy that he's claiming, and what he's shown in his 2019 paper that performs everything, if that's true, then I think we're making a good step along the right way. Now, that's not going to solve the big data problem, right? But it's still going to solve a lot of other small data problems.
Absolutely. And I want to know more about this chip. And I very much regret the fact that I didn't know about it until the end of the interview.
One thing that I'd like to add, not to be on anyone's side, is that everyone that writes low latency and low power consumption in the paper should then give the low latency and the low power consumption in that paper. So we don't have the figures of lots of papers and peoples and chips, you know?
So an interesting aside, which is kind of like a reality check for me, right? So a group of us went to speak to a DARPA director not long ago. And we were selling an idea that one of the primary focus was, it was basically extremely low power. And she could not care less about the power. She cared mostly about latency. That is the thing. She basically said, I will burn all the power I need to. And this was an embodied AI application, Giulia. She said, I will burn all the power that I need to if you can get me the speed, the decisions to happen as quickly as possible and as effective as possible. Which, for me was like what? I expected that the power efficiency argument would have been a winner on the day. It was interesting to me. We were trying to argue for like small drones with small brains and so on. And she was like, but what's the latency? When do you make the decision? Anyway, very interesting.
Let me add that I have a course that I lead here at the Czech Technical University for the Journal Club. And there was this guy that was talking about this swarm of drones. And the model was super complex. And I was there listening to this amazing paper. I was like, what do I do with my life in neuromorphic? Like it was very nice. It was working very nice, avoiding all of the others. And then at the end, after 1 hour and a half of talk, it says, oh, yes, but swarm of drones are flying for 11 minutes. And I was like, what are you even bothering? And this paper is on science. I mean, what are we even doing? So honestly, yes, the latency is important, specifically for human-robot interaction. I think that we catch and we need very good latency of the response of the robot, but the power consumption also makes a difference because now we have plenty of robots doing very complex things for 2 minutes.
Yeah, I mean, that was kind of how I went in. That was my argument.
Okay, guys, I think we got it done for today. Thank you, Sunny, again for another great interview, and Ralph for your valuable comments as usual. In the next episode, Sunny will be talking to Neuronova from Milan, Italy. We hope you will join us then.
That brings another episode of EE Times Current to its end. Thank you for listening, and thanks again to our guest, Professor Chris Eliasmith. EE Times Current is available through all the major podcast platforms, but if you get to us at our website at eetimes.com, you'll find the transcript, along with direct links to the other stories we've mentioned and other resources. Thanks for listening.